Welcome back to Made Up of Wires, where we're decompiling Castlevania Symphony of the Night. We're going to do something a little bit different today, at least for a while. And then we'll see what's next. If you have been watching recently, we've been working on Castle Keep, known as Top in the file system. And we were stuck with two instructions that didn't match yesterday, and of course, right after the stream, I was able to get those to match. Posted about it in Discord. Go to soten.z.dev, find a link to Discord. And it turns out that there are other places that this probably helps too, and actually some other places where we're not using this technique and probably need to be to get matches elsewhere. And I'll go over that as well this morning. So what I think we're going to do, though, after we look at those last two instructions, is go through some of the GameShark codes that are in soten.dev, as well as many other places around the internet when you're looking for cheats and hacks for Symphony of the Night. Often they come in the form of GameShark codes, and we're going to look at those, see how they work, and what effect that has on the code, and we'll even try to decompile some of them. Though I don't know to what success we'll have, and we probably can't get a matching decompile, but we'll try it and see. So in one case, it may actually work. We will see. So let's get started. We're going to look at Top first, and then we'll keep going. So when we left off yesterday, we had a page, or a match that looked like this: 560 differences, 99.47% match. Two instructions here that were swapped. We needed this move in the branch delay slot of the jump and link, and this jump and link seems to be aligned on a 4. They're all aligned by 4. Why is it important that there is a NOP here? I don't know. Because the previous branch equal to 0. That's right. So basically what we're saying is we want that move to be done in the previous branch delay slot as opposed to the later one, or before the function call. So how do we get that? And it turned out that somebody had already solved this in a different area, and I figured it out not by looking at that because it seemed nonsensical to me, but by looking at the PSP version and what the PSP version was doing. So the PSP version is different. There's an additional castle flag that's being checked. There's some additional settings that are being checked. But one of the things that I noticed is we're calling the equivalent function cutscene skip. It's being referenced 4 times. And when a function is referenced multiple times in the unoptimized PSP version, that means it likely shows up that many times in code. So we don't have all these branches, though, but we do have something like it. And our branches actually look a little bit like this time attack check, as well as one of the settings checks, this one down here. So I thought to myself, what would this look like if you broke that up? And so that's what we're going to do. We're going to take this outer condition, make it independent of these other predicates. And then we're going to do each one of these individually. So if time attack is unlocked, we're going to skip the cutscene. Otherwise, if that setting flag is set, what are we going to do? We're going to skip the cutscene. Logically, this is equivalent. No difference. If this first condition is true, or the second condition is true, we're going to execute the same code. The optimizer knows that it's the same code being optimized, so it only puts that in once. If we optimize that PSP version, we would probably see the same thing where all 4 of those branches lead to the same thunk of code. But also, the predicate logic of if is cutscene done and not skip cutscene and time attack unlocked or the settings, that still holds, and that predicate logic is still encoded here, just in a very different way. And it's different enough that the optimizer then moves that instruction up in the branch delay slot. It moves up in the branch delay slot because it says, probably an earlier optimization pass says, in one of these branches, I'm going to have to put self in the A0 register. In another one of those branches, I'm going to have to put self in the A0 register. So 2 of the 3 branches, the third being falling out of both of those and not doing any of them, I'm having to do this. So regardless of what happens in this first branch, in my branch delay slot, I'm going to stick that in a register because I know that 2/3 of the cases are going to need that in that register, and so I'm going to do it early. And I think that's what the logic was there. Does it change the performance or even increase or decrease any instructions? No, but optimizers are a bunch of heuristics that all kind of work independently, and they don't always do things the way you think or work together in ways that you might think that they work out. So anyway, kind of an interesting change, and that fixes everything. And then we're done. That was the end of top. I still have to clean up the code that's there. I do have a branch ready to go with the last 3 functions that all of them were done at least partially on the stream. And so probably tonight or later on today, I'll go through this and make sure that everything is up to my low standards and hopefully SozuD's higher standards, and try to push out a PR that won't be too contentious. Most of this code, sometimes I do fix things that are in shared code. This was largely taken from existing cutscene implementations, so I don't usually tweak it too much. And if I do, excuse me, I might change this is cutscene done to a true instead of a equals 1. But if that's the case, then I will usually backport that to the other ones as well. But that's it. That was cutscene. So let's get on to the meat of today, which is looking at GameShark codes and seeing what they do and how they affect the game. So we're going to do a couple things. Excuse me. We're going to look at what memory addresses are affected, if that's code, if it's data, what the code looks like if it's code, and how it changes. And I'm going to be putting at least some of these in the Soten.fun wiki. Let me save this page that I've started already, and I'll drag it over here. We'll kind of flip back between them. So this is the debug print message analysis. So we have all these GameShark codes. This is the original assembly from the game. This is how it gets modified. And then if we would consider the C code that's there, there's more C code here than these instructions, but effectively we're getting rid of this first check of game state and replacing it with a call to font flush. Unfortunately, we don't have font flush decompiled. It's part of the PS1 SDK, but we will take a look at as much of that. So let me, I'm going to drop into DuckStation. There's a few things that we're going to look at. First, I guess we'll look at the assembly. So what is a GameShark code? What does it consist of? GameShark codes are 2 parts, and they're actually pretty simple. The first is an address. The alignment is 2 for these addresses, so it's always going to be 0, 2, 4, 6, 8, A, C, or E as the last character. The rest of it is an address, and this first digit here specifies, the high bits of that digit specify the addressing mode of the system, whether to look in cache. I have a page actually open somewhere. This is a good one. So we look at how the memory map is laid out. Depending on how that first, those top bits are set, is basically how we are going to read memory. And I think, yes, this down here says what that means. So if we're reading kseg 0, for example, that is cached memory. So we could write to 0, 0, we could leave out the 8 altogether, and it would write to the same place. Let's see if any of these other ones are relevant. I don't think so. So we'll go back. I'm going to take this back to where I had this. So I'm going to be using a MIPS converter and some other tricks along the way. But we'll look at the code first and then kind of go into each of these. So we need to start here at address 3D5C. I'll just use the last 4 nibbles. And what this is saying is go to this address and then write this 45BF value. Then go 2 bytes later and write OC00. So together we've written one 32-bit value, and then go 2 bytes later and write FFFFF, and 2 bytes later and write 2404. And so we're going to see what each of those are. Actually, I'll probably pull in the MIPS converter so we can see what those are. So we need to remember as we're going through this that this is the PlayStation is a little endian. So when we write to these addresses, instructions are pulled in 32 bits at a time, and then the bytes are reordered back to front. So if we write 45BF 0C00, we're actually going to read 000C BF 45. So let's take that. I happen to know that these are instructions. They could be memory. How do we know that they're instructions? We actually can look at the decompilation. Or the disassembly by SPIM. So let's do that. Let's take one of these addresses and we're going to look. We don't necessarily know which overlay this is in. And hopefully it's in one of the overlays that we've done. But let's assume that we don't know that yet. So in this case, we've extracted things that are in ASM-US. We have at least one of each type of overlay done, so all of the addresses that SOTN is going to load data into, we have some example of. And so we find that address in exactly one overlay. If it was a stage or something where there are many, we might find it in many overlays. In this case, it's in DRA. There's only one DRA that occupies one specific space in memory. We have main that gets loaded first. Main loads DRA. DRA loads RIC, and it loads weapon and servant and stage overlays that are later in memory. But DRA stays there forever. It gets loaded once and stays there forever. Never overwritten. So we have this address. It's in a function which tells us that this is code. And our original code is a branch not equal. It's looking at V0. What is V0? V0. Sorry, V1 and then V0. We'll look at V0 first. V0 is 2, where ORing 0, the 0 register is always 0 with the value 2. And then V1 has the value of game state. So what is this code? Unfortunately, we don't have the correct symbol for this function, but here's what we're going to do instead. I happen to know that this function is, right now, we just have the generic function. The way that we'd find out what this function name is to go to the build and look at the DRA map. And that tells us that this is main game. Then we're going to look for main game in DRA. And we could find that there. It'd be nice probably if it, since it is the main game, it had a nicer name, but that's what it is. And when we were looking at the original assembly, that original assembly was loading this game state variable. So let's see if we can find where that game state variable is loaded. It's actually only loaded one place, and it's comparing it against, in this case, gameplay. We know in the original assembly that it was comparing it against a value of 2. Let's just verify that that game play, it's an enum in this case, is the value of 2. Enums, if they're not specified, they start at 0, 0, 1, 2. So that checks out as well. So now we have, we know what line that instruction is associated with. If we had debug information, like with the G option, we'd be able to see that as well. We could also throw this into decomp.me, and we'll do that in a little bit after we change it. And we can see what it's like there as well. So that's the first instruction that it changes. It changes BNE. And then it changes the next instruction as well. The next instruction was originally a NOP, which is a no-op. No-ops are encoded as all zeros. And it means do nothing. When you have a branch or jump instruction, the instruction following it always gets executed before the program counter gets updated for the branch, because the branch has to do some logic that consumes its main instruction, and the result of that logic updates the program counter. And so the next instruction is executed as well. So overwriting the NOP is not terribly dangerous, depending on what we overwrite this to. So how do we figure out what we're going to overwrite this to? So we have to take our values that we're going to write there, and we're going to put them in backward order, little endian order. I'm going to open up a page so that I can copy and paste things without flipping around too difficultly. Oh, I have it in here already. So this is actually a little strange, because when we write the bytes using the GameShark code, we're specifying them in little endian. No, what are we specifying them in? The order that they're specified in GameShark basically is how they're going to appear in memory. Let me give you an example. We'll look at what this looks like in DuckStation. Before I do that, we'll do the MIPS converter. MIPS converter converts this to JAL, jump in link, and then an address 45BF. Unfortunately, MIPS converter is not aware of some of the changes for the PSP. So this would look like jump to this address, but that's not how the PlayStation works. It takes this argument, the last 26 bits, shifts them over to the left by 2 bits because everything is aligned on 4-byte boundaries for instructions. And then the top 4, so we have 28 bits then. We need 32 bits for the whole address. The top 4 bits come from the current program counter. And so we're using program counters in the 8,000 range. So we're going to get that 80. The 8 from the program counter. So let's take this. I'll put it in a calculator. I do have a calculator here. And OBS is still around. So we're going to take that address, we're going to shift it over 2 bits. And that gives us 116FC. And then we're going to OR that with 8000, 1, 2, 3, 4. And that gives us our final address. So what is that? So we're jumping and linking to something at that address. Do we have a function at that address? So we're going to go back to the terminal. We're going to hide the calculator. There we go. We're going to look for a symbol that might exist at that address. So I like looking at the map files for things like that. It's possible that it's in assembly. We could look there as well. We actually do have something. It shows it right away. Font Flash. We can look at a map file too and build US map. Several overlays have a matching symbol, but where that symbol is defined in main. So this is a PS1 SDK function. Okay, so we have a couple things. Now we know that we're calling a function jump and link. That function is font flush. And now what do we do? What do we do with that information? We need to figure out what the next instruction is, because jump and link is going to execute the next instruction as well before it goes into the font flush function, because that instruction is in the branch delay slot. So we have another one, and we'll take those 2404, we'll throw them in the MIPS decoder again, and then FFFF. And what is that doing? That's adding the value 0 to the immediate value FFFF and putting that in the A0 register. A0 is used for function arguments, the first function argument. So our function was font flush. FFFF, depending on whether we're talking about signed or unsigned, if it's signed, FFFF is going to be -1. And so what that looks like then is, instead of checking game state against gameplay, we're actually getting rid of that altogether and calling font flush -1. And like I said, we'll go and try to disassemble this in a second and see what the instructions look like and see if we can get a matching decomp with those changes. Right now, let's see what the result is. We can see on Soten.dev what the result is, but let's look at Workstation. And we'll try to prove that this does what I say it does. So what does font flush do? Font flush is going to take things. We have a bunch of FNT print or font print functions throughout, but nothing ever flushes those to the screen. And so there's a lot of debug information that functions will print out. You can see some of it here, what the current step is. We saw these with Doppelganger, what the BAT's intermediate step is, what Doppelganger's thinking step is. So we get a bunch of debug stuff that the devs would have used. Why here? Why are we checking this instruction? We'll get to that in a little bit as well. So let me try to align my windows in a way that makes sense. I've changed how I'm capturing DuckStation because there's like a million windows in DuckStation, and we need them all. So we have our debugger. I'm going to jump to that address. So here's our original branch not equal to v1 v0, and then this is just an address later on that it's going to jump to. And then I have a cheat that I called font print, which is the same as this debug GameShark code, and we can look at that as well if we go to edit that. That's just the GameShark code exactly from Soten.dev. Actually, I'm not sure if I originally got this from Soten.dev or not, but yeah. So if we enable that, and then we go back to the debugger, now these have changed, and we have our jump and link to that 116fc function. We have our add 0 and -1 into A0, and we can put a breakpoint here. We don't have to, but let's see what happens to the game when we unpause. So immediately we get a bunch of debug information. And of course I did an item crash leaving there, but it does what we expect. And depending on the room, that debug information changes because different entities in the room are going to display different debug information. When we turn it to bat, we see that its step is changing. Kind of cool. Okay, so that's the first one. That one I went through and did already, and was kind of pre-canned, pre-prepared. So let's move on to another and see what we can find. I'm gonna go through these and find one that I may or may not think is interesting, and or more complicated. So this one also is kind of the same thing, additional drawing information, blank info. This is somewhat interesting. It's going to draw tile sets. Level select we don't care about. I like this one, the Hitbox viewer. I haven't looked into this yet, but let's see how it works. And we're going to do that together, and I've not looked at this previously, so we'll learn together. At the same time, I'm going to try to keep this Soten.fun wiki up to date, so I'm going to be typing on the side, so excuse me while I do that. And I'm just taking that GameShark code and copying it over. So this, to me, looks like it's most likely memory. It's most likely modifying values as opposed to modifying instructions. And so there must be something that's checked at render time, maybe by the render entities function, that we're enabling or disabling. So first I'm going to take this BD1C0 address, and I'm going to, again, first I'm going to look in ASM US. This is the US version of the game, and see where this is defined. And it's part of sound data. It's actually, I think, part of the scratch pad, but we're gonna see. We'll pull that out, or open that up, I mean, and see what else is around here. It is the start of something. Let's see if the map file tells us whether this has a name or not. Let's see, this will be in dra.map. It's called debug enabled. Easy enough. And what about the other address here? We'll just go right to the map file for this one. Debug hitbox view mode. And so let's see where hitbox view mode is referenced. I'm assuming that it's only in DRA, but we could look at everything just to make sure. And it is only referenced in DRA. So there is a way to trigger this in code. There's 5 different view modes, at least, for that value. So basically we can increment it until it gets to 5. So if the debug flag is enabled and we're not in palette viewer mode, we can hit X on the second controller, and that will cycle through view modes until it gets to 5, and then it'll go back to 0. So that's kind of interesting. Let's see where else this is used. So this is where it's initialized. And so here's our code. If we're playing the game and debug is enabled, so we do need debug enabled for this to ever be considered, then we're going to draw the entity's hitbox. And the code for PSP is similar. I'm a little curious as to why this condition is written the way that it is. But it looks like, at least for PSP, it's the same way. Sometimes we could tell on the PSP if that's a separate statement or not, separate condition, as opposed to combined through predicate logic. So let's do that. This one we don't have to modify or create a GameShark code. We can, that's fine, but we could actually just edit the memory to do this. Either way is fine. No, the advantage to creating the GameShark code is we have it for later. So let's do that. Actually, I think that's a good idea. So I'm gonna add a new code. We're going to call this enable hitbox viewer. And we're going to throw that in there. I don't know if you could have comments in here. It would be nice if you could. And I'm going to create the inverse as well. So I'm going to make a disable box viewer. And we're going to do the same thing, except this time we're going to make these zeros. And we'll save that. So we're writing, we're writing these as 16-bit big endian values. But no, we're writing them as 16-bit little endian values. So the bytes get swapped. The 0, 1 is going to come first. We're only writing the first 16 bits of a 32-bit value, but having the 0, 1 as the first byte is the same in 16 bits or 32 bits, which I guess is an advantage to little endian, even though I don't like it. And so we set the value 1. So let's go back and see what happens. I think I'm going to reset my state. So I don't have a disable for the other debug text. So I'm going to load where I was, and then I'm going to we'll do enable hitbox viewer, and then unpause. And there we go. So we have debug turned on, which gives us some additional things, but we have hitboxes as well. And why does item crash keep going? And so for like the wolf jump, for example, I won't be able to do it now, but if you were gonna do the wolf jump hack, you have a very clear view of your hitbox that you need to get around to be able to do the Richter skip, for example. We can go down and see the Fleet Riders and what they look like. See our items, we see... Oh, I don't have... What do you use? So enemy hitboxes are white. Alucard's hitbox is much skinnier than I expected it to be. But we see if we hit like the beak, for example, or the feet, those are not hittable areas. Our weapon in green. I don't know if there is... we can keep looking at it. I'm not sure if there is a hitbox for surfaces, but that would be nice as well. So unfortunately, the way that this is written, we don't get both the ability to turn hitboxes on, but have other debug information off. And so we might have to, if we wanted that possibility, we would have to replace that debug check in a similar way, and we could write a, that might be worth doing, write a GameShark code to disable debug, allow disabled debug, but keep hitboxes on, for example. So if we didn't want this text, but we wanted to see, and then actually might be a good thing to try doing. Let's take a look at some of these other codes and see what we can learn, if anything. Where'd my window go? So hitbox viewer, that one's pretty neat. He doesn't have debug messages on. Oh, that was my fault. I had the font print one on again. So you don't necessarily have to see messages. No clip mode. Mozilla came to the rescue with that one the other day, so you don't run into surfaces, walls, and things like that with no clip mode on. And again, that's just a memory change, not instruction change. Let's see, toggle layers. This looks like potentially an instruction, so let's go here and see. We're just gonna look at ASMUS. Yeah, so this is an A function as well. What function is that? So the original code is calling another function. So this is part of main game as well. And it's a function called to debug update. And my guess is, okay, so we have a second controller toggle. And so one of the notes here on Soten.dev is this code is currently incompatible with the tile set color lookup table viewer, and that's because these likely edit the same or similar areas. Let's go back up and look at that one. So BD1C0, and this one down here is E3D00. That's where. So they're editing the same thing. We're going to figure out what is being edited and why. So again, this is in another modification to the main game loop. We're looking for a call to debug update. And that is right here. And so instead of calling debug update, we're going to grab this, we're going to throw it in the MIPS converter, see what instruction we're generating, take that space out. This is unexpected. Let's make a. Sometimes I'm not happy with MIPS converter. Let's look at. We'll look at DuckStation and see if that is what this actually is doing. So first, I'm going to find the area in memory. We're going to jump there. So here's our jump and link to debug update. It'd be nice if you could give, there's a bunch of things that I think would be nice if we could give DuckStation symbol files so it could name these. All right, so we have our address. I'm going to put a breakpoint actually right there. And then we're going to go add a new cheat. And this one we're calling toggle layers. And so now when we enable that, our jump and link, it just changes. So it still is a jump and link instruction. It's just going to a different place. Did I copy and paste this wrong? Is that? Oh, I did. I did it in the wrong order. It's the second one first. That is what happened. Little Indian and multiple multi-byte values always screws with my head. There we go. Jump and link. That makes sense. And again, to get the actual value, we have to shift it over by 2 bits and then set the top 4 bits based on what the program counter has. And that gives us our final value. So we have a new address. Our new address is this 801 424. There's an F somewhere in there. Let's look at what that new function is that we're calling instead. I'm gonna look at the build. It's an unnamed function. You just call it 142f. How this was found is beyond what I think I can comprehend at the moment. So this function is called by at least one other caller, but it's only called. So the function existed in the PlayStation version of the game. It's never referenced in the PlayStation version of the game. But the author of SotenDev found this function. And what does this function do? Changes the tile map based on pushing different buttons on the second control pad. I'm going to try to configure a second control pad. DuckStation has not been happy with me with control pads lately. I do have another one. Do I have a cable for this? I don't think I do. Oh, crap. I need a micro USB cable. And I happen to grab one. It works. I don't know if this is going to be the best controller, but it is the controller that I have. It's a 8-bit do. 8-bit do. How do you say it? M30. So let's try to configure this. I think I'm going to do Z and C. So it's a Genesis 6-button controller with 2 shoulder buttons. So I guess a Saturn-ish controller. I'm going to try to map XZ as L1, L2, and then the shoulder buttons as L2 and R2. Let's see if I can do that. It is on. Go to controllers. Which one is SDL2 and SDL3? We're going to try SDL3. We'll make this a digital controller. Okay, so I am able to grab the right one. So it looks like that should all be fine. So let's unpause. We hit the breakpoint. I don't need that anymore. So this is pretty wild, I think. Yeah, so we can cycle between which ones we want. So what this is doing, let me just double check. And so let's go look at the code for that function. So SotenDev author, as he was looking around, or whoever came up with this code, found that there was something looking at controllers and then modifying tile map flags. I mean, you'd have to go through so much code to find this and know a significant amount about the game before we had a lot of this decompiled. How, I mean, this is pretty amazing to me that that this would work. So we can look at this code and see, so R1 is going to set one flag, L1 is going to, XOR is either basically toggling each of these flags. And then background layers we can do with L2. So let's look at that again. So this is our L2. I'm not seeing any change with R1 and R2. So that there should be certain tile maps that my regular controller is now no longer working. Oh, Duck Station. I didn't unplug it. It still is STL0. Why can I not control? I feel like this happens frequently. Yeah, so I'm not sure what's happening. We don't need to treat this as an analog controller. Digital is fine, but yeah, so now I can't control a la carte anymore. The original, going back to like what was this doing originally? We were calling debug update. Oh, that likely is what the cause is. So when we do that, we're no longer updating the game. So this this other function that's called has no return value, so v0 is going to be equal to 0. And so debug update, that is going to fail. So my guess is that this always returns 1. So we're never running the next frame. So this is kind of a suboptimal implementation. I'm not sure why this particular address was chosen, because there's probably other things that we could replace instead of debug update. So, for example, the game state check being replaced earlier. And there may be others as well, but now that we know what code does what, it's much easier to identify a check that may be superfluous. What else could we do? So we're calling a function. We're not in control of v0. v0 is going to be set by the caller. But if the caller doesn't return anything, will it set v0? Let's check. So let's go look at the assembly for 1424. And what we're looking for is whether or not V0 is cleared. V0 is not explicitly cleared, and so it's, let's try this. We're going to set V0 to 1. Or something other. Oh, thank you. Hey, Highlander. We're going to set V0 to 1. We're going to use, let's see. We can use XOR with register. Is V0 always set to 0? Find a 0. We don't have that. What about or can we use MIPS map or MIPS converter? So we want to or immediate V0 0 1. Oh, just do it. Ignore my commas if you need to. I don't know what it uses for the 0 register. Oh, there we go. Okay, so here is going to be our, this is not typically how return instructions work. Usually you don't put anything in the branch delay slot of a return instruction, but we're going to do it anyway. And so what we want to do is basically say that this function is returning a 1. So I'm going to, this may fail spectacularly, but it'll be fun to try. So we're going to enable our breakpoint here again. And we hit it, we're going to step in, so that's going to execute the next line, because that's the branch delay slot. And then that's going to take us to this function that's monitoring the controller input. And so we're going to scroll down, and this function is the same as this assembly here. And so we're going down, there'll be a load upper immediate, store word, return, no op. And so we're going to replace the no op. Carefully. So basically we need to scroll until we find that JR instruction, which is here, and then our no op that we want to modify. And I'm going to just double check the order, byte order. Make sure that I get this right. And let's see if I can edit directly in here. I can't edit directly there, but I can edit here. So we're editing 14C8, okay. So we're gonna do 01, 00, 02, 34. And now when we reload this, yeah. So we're loading, we're ORing 0 with 1, which results in a 1, and we're storing the result in v0. So the hope is that this is going to re-enable controller input and allow us to both change the layers of the game as well as continue to play the game. So I'll undo my breakpoint. And can I move? I can move, and can we still swap layers? Yeah, we can. Let's go to a different area. Every time we switch, we're gonna have to do this because the flags are gonna get overwritten. And what I want to do is come down here and look at some of these others. Can we find some of these other layers that couldn't be disabled before? No. Yeah, that's unfortunate. So really it's only that mid layer. But that is something. So how would we turn that into a how would we turn that into a GameShark code? So we found our return address. We can go, let's see, we're going to go here. Our return address is this C8. So we're going to take that and we need the first 2 bytes in little endian order, which are going to be 0100. And then the next 16 bits is going to be 0234. So let's look at this F14C8 address. We'll jump there, and we're going to put a breakpoint to get back to it easily. Wrong scenes. There we go. Go add a cheat. This one will turn off toggle layers. We're going to edit the toggle layers one. So we want to add our 4C8 address. The first 16 bits of that. The second 16 bits of that. And we'll save that. And I just want to look at it one more time. Is that what I want to see? I don't think that's what I want to see, but we're gonna, so again, my failure to little Indian. So 34020001 is what we want at the end. Let's see what happens when we enable that and what this line looks like. We're going to enable toggle layers. We're going to go back over here, and yeah, I did that in the wrong order. So I need to swap all those bytes, of course. Let's go back and edit that. Okay. So it applied it already, and we have the right thing. So we went through, looked at toggle layers, which I'm still baffled by how somebody would go, excuse me, go about finding that. And we were able to augment it with some additional logic so that we can keep playing the game while it's there. Pretty cool, pretty cool. So yeah, that's a little bit about how GameShark codes work. We have an address, we have a value. There's 16 bits at a time. if we have the code for the game, if we have a disassembly of the game with that code, we can not only see what that's doing, but we can make our own pretty easily as well. So let's do one more thing. I said I wanted to look at what that first one, what it would look like from a perspective of a decompiler. And so we're going to go and we're going to re-enable that. I'm going to grab those instructions. Actually, I have the instructions over here. So here we are in the main DRA main, and we have all the code for that. Am I going to be able to pull all that out with enough context? We'll see. What do I want? Oh, I don't need DuckStation right now. We're going to go get rid of that. We're going to look at main game, which is where that change was made. Let's see. That will be in soten.fun. So originally, the code is checking game state for the gameplay state, and it's changing it to font flush. And so originally we have these instructions, branch not equal, and then a no-op, and we're changing those instructions to jump and link along with these others. So what we're going to do is find that assembly. So the assembly you can get just by having the game, running it through a disassembler like Spim. We do it using Splat, which is a wrapper around Spim, among other things. It does more than just wrap it, but Spim is the disassembler. So it's pretty, you don't get all the symbols. We've added most of the symbols. Some of the symbols are part of the PlayStation SDK. But you can get a lot of this basically for free if you have a copy of the game. So originally our instructions was BNE. We're going to replace this. We're going to change this to a jump and link, and we're going to font flush. And then we're going to change the delay slot function from no-op to add immediate unsigned. Store it in A0, add the register A0 to the value -1. And we can change, these are comments, so we could change what that means, but it's not terribly important. So we're going to, I think I wrote that. We're going to copy that. We're going to go to decomp.me, just like we would normally, which is open somewhere, I'm sure, in all of this mess. Start a new scratch. This is the PlayStation US version. Paste our new disassembly. And we have a bunch of symbols and other things like that that we don't know. But I'm not worried about any, like, we're not going to do this from the start. What I want to do is grab existing code, and I should have actually a lot of the declarations already. So I'm going to grab those. And then we need a few more things. I'm going to make these declarations instead of actual definitions. And so what I want to see is, this is code that was not created by the compiler. What is the likelihood that we could actually get a matching decomp with that modified code? This will not always work. If it works this time, honestly, I'll be a little surprised. But I'm just curious, more than anything. Can we decompile GameShark codes? I think we might be able to in this case. The one thing, so where instructions, so let me back up a little bit. When you're doing GameShark codes, you're modifying existing places in memory, and you're not adding or subtracting anything. You're just taking values and you're modifying them. You can write to areas of memory that don't exist, and you could have extremely long GameShark codes which add completely new functions and then hook into them in various places. There was a comment, I've mentioned it several times, about the Maria mod that Zyynamo was able to do. Let's see, 117. Okay, so all of these are things that we do need. So we're going to grab each one of these. And get those definitions. Somebody said about the Maria mod that they had a GameShark code that allowed them to play Maria in the original PlayStation version. They definitely did not. That is quite impossible. Nothing like that could have been done with the GameShark. So if you ever hear somebody say that, you can say, I have no idea what you're talking about. There was no Maria in the original. So I'm just grabbing each of these variable declarations so I can get the original to compile. This can be tedious, but it needs to be done. Almost there. So we need the debug mode struct. So I'm taking all these and just copying them into the scratch in decomp.me if you're trying to follow along. We need a debug color channel. Almost there. One more, I think. So off the bat, 98%. So what I'm expecting and hoping is that the only place we have a difference is, so we have symbol differences, not concerned about that. What we should see though is around this game state 261, that's where we should see a pretty significant difference. And by significant, I mean 2 instructions. And we can look at what M2C would do for its decompilation and see if that looks like what we think. And it actually doesn't look too bad. So let's see if that ends up working. If we can just replace that and decompile that way as well. So we're going to take out this check, which was replaced. And we don't. Okay, so this is interesting. We're never going to be able to compile this because so this will never match on GCC. We're keeping these, but it also tells us we have 3 additional instructions that we could do something with, because now these are superfluous. We don't need to load the game state variable anymore, or global, because nothing's using it. We don't need to load an immediate value of 2 because nothing's using it. We can't force that in any way because that would be dead code. So basically, there's nothing we could do. We could never match that decomp. I am a little impressed, I think, that the font flush generated instruction put the argument in the branch delay slot, exactly like the GameShark code produces. That's cool. But basically we're stuck. We would never be able to get a matching decomp here, and that's not the goal, is it? It's really just to see what that change looks like if we put it through the same process that we're doing for the regular game. So that's pretty cool. I'm happy with where that ended. We got to create some new GameShark codes. We got to look at a bunch of different ones that change memory, that change instructions, and how those affect the game. Pretty neat. I remember being a kid, I didn't have a GameShark for the PlayStation. I did have a Game Genie. Game Genies were a little bit more magical because they encoded their addresses and values in ways that made them seem mystical. And I remember being in computer science classes in the late 90s, early 2000s, and realizing how Game Genies worked, and just marveling at the cleverness. And now you know how Game Genies and GameSharks work by mapping addresses to values. So let's look at what is next. We need a new overlay. Let's go look at GitHub and see what's next. I think I threatened to do RTOP next, and I think that's probably not the worst idea. We don't have, except for reverse warp, we don't have any of the reverse castles started. The odd 100% there. So we will be at 100 for Castle Keep soon. It might be fun to go back and look at some of the difficult ones too. Like there's a function in cell that doesn't exist in any of the other versions of the game we've come across so far. Is that something that we can do something about? Actually, do we have cell for HD? That might be worth looking at. So we do still have some regular castle stages that are yet to be started. And I did start looking at Weapon 1. Not sure what to do about that yet, so I think I'm going to leave it for now. But let's look at our top. We're going to just start it and then do a little bit of evaluation. And then we'll end the stream. So let me make sure that this is building fine. DRA is broken. I haven't looked at what file conflicts yet. There's a file that's overwritten when you extract the PSP version or build the PSP version that breaks DRA. And so if you build both of them at the same time, one or the other is going to be broken. And that's why that one's failing, unrelated to anything that we were doing today. I'm going to look at run tools, make config, and we're going to do RTOP and see what we see. So this is going to look at the overlay, try to match as much code as possible to existing overlays. Actually, I'm going to delete everything that this does, and I'll tell you why as soon as this finishes and that I do that. When it's looking at other overlays, I believe that I wrote it to only look at some and not all, but let's double check that. Maybe it is looking at all of them now. No, it's not. So I need to add top to this list because top is done and it is valuable in this case because it may have things that are the same, like the clock tower code and things like that. So let's add top there. This mucks with your Git history, or Git staging area, which I really dislike. All right, I think that's it. So we'll run it again, and this time we have top to compare it to as well. I think it matched 109 before, so it may not have mattered much. So we have a couple tools that are run here. We come through, we look at all of the existing decompiled code, look for any segments, which are basically file boundaries that are the same between something that we've already decompiled and this new overlay that we want to decompile. And if they match, we can map all of the symbols and the names of those segments. Then it comes through, does its disassembly, then it does a fuzzy match on the remaining functions to try to give those names as well. And let's look at the splat config, which will tell us what it was able to find and how much code is unknown. So a curious split in US. I'm not sure why we got a unnamed split. But so we see the vast majority of this is things that we know about already. And how much? Let me do some. Oh, we can look at these files. Let's look at source, strtop. we'll have a us.c. So we're going to start with lock camera. That's going to end here. Then we have a bunch of new functions, one of which is the same as something that we've seen before. ST update looks like it's going to start at where? At least by the time it gets to random. And we have collision and all the others. Let's go past. So Clock Tower 3D is probably the same as the top version, or very similar. Where are our... So I think basically these two functions. Yep. One may be clouds. We have between prim helpers, so 2D5, 2D57C. So something that was named at 2D57C, 2D57C. Oops. We'll look at ASMUS ST on top. So here is new stuff down to here, I believe, which no, skeleton pieces will be part of this as well. Prim helpers is a FO280, but we won't see that. So Prim helpers is going to start there. So I think that's everything. So I have US starting there, going to ST update. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 functions at the top, 14 with the clock tower. 15, 16, 17, 18, 19, 20, 21, 22. So 22 new functions, skeleton pieces looks like it's probably a duplicate. So about 20 functions probably overall that haven't been seen before for RTOP. So that's pretty cool. That seems like another overlay that should go pretty quick. And I think we'll start that tomorrow. So that's it. What do we do today? We looked at Soten.dev and how those GameShark codes work and how they can be improved. As far as I know, the author of Soten.dev is radio silent for a while now. So if you know him or know how to get in contact with him, we can update some of those codes with one that allows you to keep playing even when you have some of these other like toggle layers enabled, and how all that worked. And then looking at RTOP. So top is done code-wise. I don't really do a lot of the data decompilation on the stream because I think that's kind of tedious and boring. But if people want to see that, we can do that as well. That's all I got for you, though. Go to Soten.dev. Sorry, not Soten.dev. That's where we get the GameShark code. Soten.z.dev is where the decompilation project homepage lives with all the progress of the overlays that we've been working on. New Game Genie confirmed, that's right. Extra gold this time. I love that gold sticker on my Game Genie. Do I have Game Genie? I don't have Game Genie. Oh, I do. I do have Game Genie. not the Game Genie itself. But I do have my Genesis Game Genie book, very yellowed from time. And I didn't have these originally. I got these, how, I don't know, but code update books. Man, what a job would that have been in the 90s to come up with Game Genie codes? That would have been a sweet job. Would have loved that. Hey, if you're a game studio and you want GameShark codes for your games, that's not a thing anymore. But if you do anyway, subscribe, hit the like button, and then comment and tell me you want to hire me to do that. That's all I got. Adios. Hey, Entropy Gravity Well, good to have you.